And welcome back. As we go ahead and look at another programming lesson, let's go ahead and discuss today the concept of references. So, to lead our discussion, we're going to look at a sample class known as the toy class, which is simply just a placeholder name for, you could call this class, of course, my class, whatever you want it to be. So, we're going to explore, of course, the concept of a reference. So, to do that, we're going to use this toy class example. Variables of a class type name objects of the class differently than how we do this with variables of primitive types, such as int, char, and how we store their values. Every variable, whether you're looking at a primitive or class type, is implemented as a location within computer memory, which we, of course, previously just looked at. So, what does it mean to have a reference? Well, for a variable of primitive type, the value of the variable is stored in the memory location assigned to that variable. So if you would go to, let's say we had memory location 1000, and you looked at memory location 1000, you had a Boolean value there. You could determine in that location if it was true or false. However, a variable of a class type stores only the memory address of where an object is located. The object named by the variable is stored in some other location in memory, and the variable contains only the memory address of where that object is located. This memory address is what we refer to, therefore, as a reference, because it's referencing the location. Now, we had, of course, already talked a little bit about some variables and how they are used in memory. Variables of primitive type and variable of class type are different for a reason. A value of a primitive type, such as int, always requires the same amount of memory to store one value. It's always going to be a set fixed value. Same thing with like double or char or any other primitive type. Now, if you think about it, there's a maximum value of type int. We can only make an integer so big. So therefore, because they can only be so big, values of type int have a limit on how big they can be. Same thing goes with our other primitive types. However, for an object of a class type, such as an object of class string, well, these might be any size. The memory location for a variable type string is not of a fixed size, so it cannot store an arbitrary long string. Right? It can, however, store the address of any string because there's a limit to the size of the address. So we do have some limitations that we still have in place even when we start looking at class types. So let's discuss these memory addresses just a little bit. Because variables of class type contain a reference, such as a memory address, two variables may contain the same reference. And in such a situation, both variables name the same object. So this would be taking one object, for example, and set it equaling to another object. Any change to the object named by one of these variables, whether it's the first one or the second, will produce a change to the object named by the other variable. Because, in effect, they are the same object because they're referencing the same location. So let's start by looking at an example to really give us some context. Consider the following code. Toy class variable 1 equals new toy class Joe42, toy class variable 2. If I set variable 2 equals variable 1, now both variables technically name the same object. And if I say variable 2 dot set Josephine, 1, and then I do a print line of variable 1, it's just going to invoke the toString method for variable 1. This would, of course, output Josephine 1. It's interesting to note this because if you remember, variable 1 was set to Joe, and the only thing we set was variable 2. However, the object for variable 1 was changed without ever having to name it, and that's because, again, they're using the same reference. Now, assignment with variables of a class type is not the end of the world here. We just have a little nuance to handle here. You'll note that when you're using the assignment operator, equals, with variables of class type, you're assigning, therefore, not the value, but a reference or memory address. So the result of the following is to make variable 1 and variable 2 names for the same object. So we say variable 2 is equal to variable 1. We're effectively saying these are two different names for the same thing. A variable of a class type stores a memory address, and a memory address is therefore a number. However, a variable of a class type cannot be used like a variable of a number type, such as int or double. And this is intentional, all right? We don't want it to act like a primitive type because that could open up some real big complications with how we are using our code. We want to keep those two things very distinct. The important property of a memory address is that it identifies a memory location. The fact that the implementers of Java use numbers rather than letters or strings or something else to name memory locations is kind of an accidental property. Java prevents you from using this accidental property, though, to stop from doing things such as obtaining access to restricted memory or otherwise, just kind of messing up the computer permanently. So you don't have to worry about this potentially happening. And now let's go ahead and pop over to Eclipse to take a look at how that code is going to look. If we look real quick at our toy class, we can see we have a pretty basic, straightforward class here. We have two private variables. We have name and number. We have a constructor here that's going to parameterize them. We have no R constructor. We have a set method, a toString method. We have this method called changer, and we have a method called equals. So pretty straightforward. If we look at our demo method, this is of course the code that we had looked at previously. We see we have our toy class variable 1 is set to a new instance. Toy class variable 2 we declare, but then we set equal to variable 1, and then of course we do .set Josephine. So if we run this, we should of course get the exact same output that we previously had seen. And so we get Josephine 1. Now, this again we know is because there is a issue where both variables are pointing to the same location in memory. But what if, let me just go ahead and just copy this. What would happen if I were to instead say this? What if I make this a new toy class object? I'm going to set this to Josephine, and we'll make it 41. Now let's just comment out our set line here. Is this going to change anything? Because now we're saying variable 2 equals variable 1, but you notice both are instances of a new toy class object. Will it change anything? Well, if we go ahead and run our code, we see we now get Jo42. It did not become Josephine. All right. What if I made this variable 1 and this variable 2? All right. Now, that would mean, of course, even though we're changing those, when we rerun this, we get Josephine 41. Because what variable are we printing out here? We're printing out variable 1. Variable 1 gets updated to whatever variable 2 was. And this is okay because we are still keeping those separate. In fact, if I were to have it again the other way, remember when I did variable 2 equals variable 1, we got Jo42. And you might ask, why is this? Why is this acting this way? Well, remember, because we are not having this simply just end, we set it to its own new instance. It allows us to say, hey, this variable right here is its own object. And so if we want to avoid having like memory conflicts like we had just seen when this didn't exist, then we have to make sure that if I did something like this, all right, now this one doesn't do anything because I didn't change the value here, so let me just set it to Josephine real quick. If we don't want this to happen, we need to make sure we initialize our variable to a new instance of a class object. And that's part of the reason, again, why we use this new identifier here on our code.